Last week, the NASA team performed one of the riskiest James Webb operation to date. They opened the telescope's tennis court-size sunshield, providing sub-zero shade for the mirror and infrared detectors.
In the vast distance of space, amidst the cosmic stage of galaxies, lies a remarkable celestial spectacle, a starburst galaxy. This galaxy resembles a thriving factory, where stars are produced at an impressive rate. NASA's innovative observatory, the James Webb Space Telescope, is expected to revolutionize our understanding of this galactic marvel by reaching deeper into the universe than ever before. But what powers these cosmic engine rooms? And what secrets do they conceal? Join us on this stellar adventure as we take a look into NASA's Webb Telescope's exploration of an extreme starburst galaxy, the incredible stellar cradle. The James Webb Space Telescope, JWST, has taken us on an amazing journey deep into the heart of the Cigar Galaxy, also known as Messier 82. It's like we've been swept away on a thrilling adventure, witnessing a breathtaking display of stars being born. It's like a magnificent galactic fireworks show, dazzling across the vastness of space. In this galaxy, things are anything but quiet. At its core lies a fascinating region where stars are born amidst chaos and beauty. It's similar to a bustling city, but instead of streets and buildings, it's filled with swirling gases and newborn stars. This compact yet disorderly domain offers us a rare glimpse into the fierce beauty of stellar genesis. As we dig deeper into this growing stellar metropolis, we're on the brink of uncovering the secrets of star formation under the most extreme conditions. It's like peering into a cosmic laboratory where colossal stars burst into existence, illuminating the darkness with their radiant light. These stars aren't just a feast for the eyes. They hold the key to unlocking the mysteries of how stars are born on a grand scale. What makes the heart of Messier 82 truly special is its compact and turbulent nature. It's like a bustling city center where the chaos of star formation acts as a boost for new stellar life to emerge. And thanks to the JWST's new infrared vision, we're able to peel back the cosmic dust and gas to reveal the intricate spectacle of this stellar cradle. With each observation, the JWST is shedding light on the complexities of star formation in this dynamic region. It's like using a powerful flashlight to illuminate the darkest corners of the universe, allowing us to witness the birth of stars in unprecedented detail. And as we continue to study the heart of Messier 82, we're on the verge of unlocking even more secrets about the captivating dance of stellar creation. The telescope has peeled away layers of galactic dust, revealing the hidden wonders of the universe. From the remnants of supernovas to areas where molecular hydrogen glows under the light of young stars, it's like discovering a treasure trove of cosmic secrets. This wealth of information is crucial for piecing together the puzzle of how stars are born and evolve within such a vibrant environment. But the exploration of the core of Messier 82, or M82, goes beyond mere curiosity about one galaxy. It holds broader significance for our understanding of the universe. By unraveling the mysteries of star formation within Messier 82, astronomers can gain insights into the fundamental processes that shaped the early universe. This journey through Messier 82 not only satisfies our thirst for knowledge, but also deepens our connection to the cosmic dance that shaped the galaxies, stars, and planets of the universe. As we venture into the next chapter of our cosmic journey, we focus on the anatomy of galaxies, particularly on the dramatic galactic winds that sculpt their structure and influence their growth. The power of galactic winds. The starburst galaxy, Messier 82, stands out not only as a birthplace for new stars, but also as the stage for an amazing cosmic event, galactic winds. These winds represent the galaxy's breath, a powerful expulsion of gas and particles driven by the intense activities at its core. Our exploration into the inner workings of Messier 82 reveals the crucial role these winds play in determining the galaxy's fate. Born from the fury of star formation, massive stars eventually meet their spectacular end in supernova explosions, injecting immense energy into their surroundings. This energy surge propels gas and dust outward, forming a galactic wind that sweeps material from the heart of the galaxy. The James Webb Space Telescope has given us an incredible view of a truly captivating phenomenon. It's like having a front-row seat to a breathtaking show, where we can see the complex patterns and powerful impact of galactic winds in exquisite detail. These winds aren't just a visual spectacle. They're essential players in the galaxy's evolution. By pushing out gas and dust, they help regulate the materials needed for star formation, striking a delicate balance between creation and destruction in the cosmos. This fascinating process, known as feedback, is crucial for understanding how galaxies evolve. By studying how galactic winds interact with their surroundings, astronomers are uncovering the secrets that shape galaxies and drive cosmic progress. At the raging heart of the Cigar Galaxy, Messier 82, stars emerge from a chaotic environment. With the JWST's help, we've peeled away the layers of turmoil to reveal hidden truths about star formation within this starburst galaxy. One of the most intriguing discoveries is the surprising similarity between the emissions of certain molecules and the patterns of hot, ionized gas. This challenges our assumptions about the harsh conditions these molecules endure, suggesting they may somehow rejuvenate despite their hostile surroundings. This revelation prompts us to rethink our understanding of cosmic molecules' resilience and life cycles, deepening our appreciation for the complex processes driving star formation and galactic development. Even in the face of intense radiation, the JWST has captured stunning images within Messier 82. The galaxy's vigorous winds and the shock waves from newborn stars and supernovas shape its very fabric, even as they sweep away the ingredients needed for future star births. Understanding this intricate feedback loop is crucial for unraveling the forces that drive star creation and transform galaxies. The insights we've uncovered from the heart of Messier 82's starburst core go far beyond just this one galaxy. They offer us a glimpse into the epic cosmic story of how stars are born. These discoveries shed light on the pathways through which the early universe evolved, enriching our understanding of cosmic history. As we continue to observe Messier 82 and other starburst galaxies through the lens of the JWST, we edge closer to unlocking the universe's secrets. With each step in our journey through the mysteries of space, we are propelled further into the narrative of the cosmos. Let's remain eager and open to the endless wonders that await us. With the unparalleled infrared vision of the JWTS, we can peer into regions of space that were previously hidden from us, witnessing the formation of the earliest galaxies. The JWST's journey to the extreme starburst galaxy offers us a unique insight into the cosmic phenomena that shape the universe. But what makes a starburst galaxy extreme? The cosmic factory of starburst galaxies. A starburst galaxy is a place where stars form at a rate hundreds of times faster than in our own Milky Way. It's like a cosmic factory working tirelessly, churning out stars at a pace that seems almost reckless. Through the eyes of the JWST, we venture into this bustling nursery, uncovering the forces driving such abundant star production and what it means to understand galaxy evolution. At the heart of a starburst galaxy are the essential ingredients of creation: gas and dust. These aren't just random cosmic debris, they are the building blocks of star formation. The JWST's infrared abilities allow us to peer through the dust that once obscured our view, revealing the intricate processes at play. We discover how turbulence within these galaxies compresses gas until it ignites, giving birth to new stars and offering insights into the cycle of cosmic life and death. Surprisingly, black holes play a crucial role in the story of extreme starburst galaxies. These massive gravitational giants, often found at the galaxy's core, can both fuel and hinder star formation. Jets and winds from black holes can either spark new stars or stop the process by blowing gas away. This delicate balance shapes the fate of the galaxy, steering it toward either quiet dormancy or vibrant growth. Exploring an extreme starburst galaxy not only satisfies our curiosity, but also holds profound implications for understanding the universe's evolution. By studying these galaxies, we learn more about the conditions of the early universe, the formation of galaxies, and the role of dark matter. This knowledge brings us closer to answering some of the most fundamental questions about our place in the universe. The JWST's observations extend beyond just the birth of stars. It also sheds light on the atmospheres of exoplanets orbiting distant stars. Exoplanets are worlds beyond our solar system, also known as extrasolar planets. They often orbit stars of their own, and some are part of entire planetary systems. Like planets in our solar system, exoplanets are made of various elements and come in diverse compositions and structures. There are different types of exoplanets. Some are giant or Neptune-like, mostly consisting of gas. Hot Jupiters are gas giants that orbit very closely to their stars, resulting in high surface temperatures. Super-Earths are smaller than gas giants, but larger than our Earth, primarily made of rocky or icy material. Earth analogs resemble our planet in size, composition, and distance from their stars. Detecting exoplanets directly is challenging because they are overshadowed by the stars they orbit. To overcome this, scientists have developed several methods, including radio velocity, direct imaging, astrometry, gravitational microlensing, and transit, which is the most common method. Transit occurs when a planet passes between its star and Earth, causing a temporary decrease in the star's light. The existence of exoplanets has been suspected for thousands of years, but the first confirmation of an exoplanet orbiting a Sun-like star was in 1995. Since then, about 4,000 exoplanets have been confirmed by various discovery methods, with thousands more awaiting verification. It's believed that nearly every star in the Milky Way may have at least one exoplanet, potentially totaling around 1 trillion in our galaxy alone. The search for exoplanets continues not only to build a catalog of known worlds, but also to explore the possibility of life beyond Earth. Astrobiologists study exoplanets' size, composition, and location relative to their stars to assess the likelihood of life existing in environments different from our own. By examining their chemical compositions, temperatures, and weather phenomena, we gain insights into their potential habitability. Through the JWST's eyes, we're beginning to discern which worlds might harbor life, marking a significant leap in our quest to answer the age-old question: are we alone in the universe? The universe is a dynamic, ever-changing place, with galaxies constantly colliding and merging. The JWST provides unprecedented views of these cosmic encounters, revealing the role these colossal events play in shaping the structures of galaxies and triggering new waves of star formation. The telescope's meticulous observations help astronomers solve the mystery of how galaxies grow and change over billions of years. One of the JWST's main goals is to peer back in time to the universe's dark ages, the period after the Big Bang before the first stars sparked to life. This part of the mission aims to capture light from the earliest galaxies, giving us a glimpse into the cosmic dawn. By studying how these ancient structures formed, we're uncovering the origins of the cosmos and the fundamental processes that shape the universe we see today. While the JWST is primarily a light-gathering telescope, it also plays a crucial role in studying the universe's darker side: dark matter and dark energy. The mystery of dark matter and dark energy. Dark matter is what allows galaxies to form and hold their shape. When we looked at how the universe is put together, we realized there isn't enough regular matter to explain it. The gravity from the matter we can see isn't strong enough to make galaxies and other complex structures. Without dark matter, stars, even in starburst galaxies, would be scattered all over instead of forming galaxies. So, we know there's something else out there, something dark that doesn't give off or reflect light. We can't directly see dark matter, but we can see its effects. Places with a lot of dark matter bend the light that passes nearby, showing us that it interacts with gravity. However, we're still not sure exactly what dark matter is. We know it's not just clouds of regular matter, without stars or antimatter, because it would produce different effects. It's also not made of black holes, which have a strong impact on their surroundings, while dark matter seems to be spread out. We do know three things for certain. Something is out there, it interacts with gravity, and there's a lot of it. Dark matter is probably made of a strange type of particle that doesn't interact with light and matter as we expect, but scientists are still trying to figure it out. Dark energy is even more mysterious. We can't detect it directly, but we can see its effects. Back in 1929, Edward Hubble noticed that light from distant galaxies shifts towards the red end of the spectrum as it travels through space. This showed that the universe is expanding, which suggests that in the future, the JWST is likely to uncover more starburst galaxies. More recent discoveries have revealed that not only is the universe expanding, but its expansion is speeding up. This is surprising because we used to think gravity would slow it down or even pull it back together eventually. Space itself doesn't change as it expands. There's just more of it. Galaxies are held together by gravity, so we don't notice this expansion in our daily lives. But we can see it everywhere in the universe. Dark energy seems to be some kind of energy that's part of empty space, and it's stronger than anything else we know. And it keeps getting stronger over time. Empty space possesses more energy than all other forms of energy combined in the universe. We have various theories regarding what dark energy could be. One theory suggests that dark energy isn't a substance, but rather a characteristic of space itself. Even though space seems empty, it's filled with energy. This energy continuously generates more space and remains highly active. As the universe expands, more space may emerge to fill the gaps, causing the universe to expand even faster. This concept is similar to an idea proposed by Einstein in 1917 called the cosmological constant. It suggested a force that countered the pull of gravity. However, when scientists attempted to calculate the amount of this energy, the result was so unexpected and strange that it only deepened our confusion.
Another theory proposes that space is teeming with temporary, virtual particles that spontaneously appear and disappear. The energy from these particles might contribute to dark energy. Alternatively, dark energy could be an unknown type of dynamic energy fluid or field that fills the entire universe, but behaves opposite to normal energy and matter. However, if it does exist, we're uncertain how or where we could detect it. Therefore, many questions remain unanswered. Our understanding of dark matter and dark energy is still in the realm of theories. This uncertainty can be frustrating, but it also makes frontier science incredibly thrilling. It reminds us that despite our technological advancements, we're still explorers on a small, fragile planet in the vastness of space, seeking to unravel the mysteries of the universe. There's still so much left to discover, and that's truly exciting.
By observing gravitational lensing and the distribution of galaxies across the cosmos, the telescope provides clues about these mysterious forces. Understanding dark matter and dark energy is key to unlocking the secrets of how the universe expands and what its ultimate destiny might be. As we continue to gather data from the JWST, we reflect on its legacy and its impact on science and society. The JWST provides unparalleled views of the life cycle of stars, offering insights into how stars and their planetary systems evolve. The life journey of a star. The life journey of stars begins with a vast cloud of dust and gas, which we call a nebula. Over time, the force of gravity pulls these particles together, forming a structure known as a protostar. As more particles collide and join the protostar, it grows larger, and its gravitational force becomes stronger. This allows it to attract even more dust and gas. As the protostar accumulates more material, gravity squeezes it, making it denser. This increased density leads to more collisions among particles, raising the temperature inside the protostar. When the temperature and pressure reach a critical point, hydrogen nuclei start fusing to form helium nuclei through a process called nuclear fusion. This fusion releases enormous amounts of energy, keeping the star's core hot. At this stage, we refer to it as an actual star, specifically a main sequence star. Main sequence stars maintain a stable balance between the outward pressure generated by nuclear fusion and the inward pressure caused by gravity. This balance can last for billions of years, as is the case with our Sun currently. However, eventually, the star will deplete its hydrogen fuel, leading to the cessation of nuclear fusion. At this point, gravity takes over, causing the star to contract into a smaller ball. The increasing density and temperature reignite nuclear fusion, causing the star to expand once more. This time, the fusion process generates heavier elements, including those up to iron on the periodic table. The extent of the star's expansion depends on its initial size. A small to medium-sized star, like our Sun, will transform into a red giant. However, if the star is exceptionally large, it will become a red supergiant. Both types of stars, red giants and red supergiants, follow distinct paths in their life cycles. Let's start by examining the red giant, and then we'll circle back to explore the red supergiant. As the red giant ages, it becomes unstable and sheds its outer layers of dust and gas. What remains is a hot, dense, solid core, which no longer undergoes nuclear fusion. This remnant is called a white dwarf because it emits a lot of light and appears white. Despite its brightness, it is relatively small. Over time, the white dwarf cools down and dims as it releases its energy until it transitions into a black dwarf, which emits no light and appears dark. Now, let's turn our attention to the other possibility for main sequence stars, the red supergiants. Red supergiants, after undergoing further nuclear fusion, begin to shine brightly again. However, after experiencing several cycles of expansion and contraction, they eventually explode in a phenomenon known as a supernova. This explosive event creates elements even heavier than iron, which scatter across the universe. What happens next depends on the size of the star. If it's relatively large, it may condense into a very dense core known as a neutron star. However, if the star is exceptionally massive, it could collapse inward, forming a black hole. The name black holes originates from their incredible density, which allows their gravitational pull to capture any nearby light. As a result, they appear as seemingly empty regions or minuscule voids in the universe, devoid of any emitted light. Observations of protoplanetary disks around young stars give us clues about planet formation and the conditions for life to emerge. The universe is a vast web of galaxies connected by filaments of dark matter, known as the cosmic web. By mapping this structure, the JWST helps astronomers understand how the universe has evolved from its uniform state after the Big Bang to the complex structures we see today. Additionally, the telescope's observations of supernovas and galaxy distribution help scientists measure the rate of the universe's expansion and investigate the nature of dark energy. Understanding this mysterious force is crucial for piecing together the puzzle of cosmic evolution and predicting the universe's fate. The search for life beyond Earth takes a big leap forward with the JWST. Webb's exploration of exoplanets. The JWTS studies the atmospheres of exoplanets, searching for signs of water, methane, carbon dioxide, and other chemicals that might indicate habitable environments. These discoveries matter in the wider hunt for extraterrestrial life and what future missions could reveal about our cosmic place. Galaxies are always changing, like living systems. The JWTS also observes the process of galactic mergers, how fast stars are forming, and the role of supermassive black holes in shaping galaxies. By understanding these movements, astronomers can piece together the history of the universe and predict what might happen next. Quasars and active galactic nuclei are some of the brightest and most powerful things in space, likely fueled by supermassive black holes at the centers of galaxies. The JWST can observe these distant bright objects in incredible detail. By studying their light, astronomers can learn about the properties of these black holes and how they affect their host galaxies, giving us insights into how black holes grow and how the universe changes over time. One of the JWST's main jobs is to observe the cosmic reionization era, when the first stars and galaxies formed and started ionizing the gas around them, ending the cosmic dark ages. By capturing the faint light from these early galaxies, the JWST helps astronomers figure out how the universe became clear to light, setting the stage for the complex cosmic web we see today. The elements that are crucial for life were made in stars' cores and spread throughout the universe by supernovas. Through its observations, the telescope helps scientists understand the entire life cycle of stars, from when they are born to when they explode in dramatic demise. These processes spread out the elements needed for planets and life to form. Recent discoveries of interstellar objects passing through our solar system, like Oumuamua and Comet Borisov, have opened up a whole new area of study. The JWST can observe these mysterious visitors, giving us a special chance to study material from other planetary systems. By looking at the light reflected or emitted by these objects, astronomers can learn more about their makeup and properties, improving our understanding of the universe beyond our own solar system. Throughout history, astronomers have discovered that stars yield their secrets when observed accurately. Initially, ancient scholars likened stars to familiar objects from everyday life. Around 450 BC, the Greek philosopher Anaxagoras theorized that stars might resemble hot stones, radiating extreme heat but located too far away for us to sense their warmth. Although this notion had some truth to it, Aristotle, a century later, held a different view. He argued that stars couldn't be composed of fire, stone, or any earthly substance because their behavior was unique. Unlike falling objects that move in straight lines, stars appeared to spin in circles as they rose and set each night, suggesting they were eternal and made of a heavenly substance called ether, according to Aristotle's perspective. Aristotle's ideas dominated astronomical thought for nearly 18 centuries until astronomers began to adopt new perspectives. They realized that it wasn't the stars spinning in circles, but rather it was the Earth's rotation and orbit around the Sun that created the illusion of stellar movement. Then, in 1572, a remarkable event occurred. A new star suddenly appeared in the constellation Cassiopeia, shining brighter than any other star in the sky before gradually fading from view. This event, later identified as a supernova, showcased that even stars could change. The invention of the telescope marked a turning point in astronomy, allowing astronomers to observe distant objects with greater clarity. Planets, once mere specks in the sky, were revealed as fully formed worlds. Moreover, the telescope confirmed that stars were much farther away than previously thought, similar to distant versions of our own Sun. This realization blurred the distinction between the heavens and Earth, demonstrating that both were governed by the same laws. Isaac Newton's groundbreaking discoveries, including his law of gravity, further solidified this connection, showing that celestial bodies like the Moon and planets obeyed the same laws as objects on Earth. However, it was another revelation from Newton that paved the way for astronomers to delve into the composition of stars. The Secrets of Lights and Stars. In his book on optics published in 1704, Newton unveiled the discovery that white light is actually a blend of all the colors of the rainbow. Using a prism of glass, he demonstrated how this mixture of colors could be separated into a spectrum, much like the colors seen in a rainbow. Newton's explanation shed light on how rainbows form, yet it was not until 1802 that an English chemist named William Wollaston took this understanding further. Wollaston refined the process of separating light colors by passing sunlight through a narrow slit and then through a prism. During this experiment, he noticed thin, dark lines within the sun's spectrum. Initially, Wollaston thought these lines merely separated the colors, but little did he know, this was just the beginning of a fascinating discovery.
In 1814, a German instrument maker named Joseph Fraunhofer invented a device called a spectroscope, designed to measure the refraction of light through various types of glass. When Fraunhofer used sunlight with his spectroscope, he observed not only the same dark lines noted by Wollaston, but also hundreds more. Unbeknownst to him at the time, Fraunhofer's invention would eventually unlock the mystery of the composition of the sun and stars. However, it would require someone to decipher the hidden message within these lines and translate them into valuable astronomical knowledge. Despite initial doubt, scientific progress prevailed. In 1835, French philosopher Auguste Comte speculated that the chemical composition of stars would forever remain beyond human understanding, suggesting that traveling to the stars would be necessary to uncover their secrets. However, the invention of the spectroscope soon proved him wrong.
The spectroscope operates by dispersing light into a spectrum of colors, revealing fine dark lines within the sun's spectrum. These lines, known as absorption lines, signify specific wavelengths where some of the sun's light energy is absorbed. In the 1850s, German physicists Robert Bunsen and Gustav Kirchhoff embarked on experiments to understand these lines further. Their findings demonstrated that when light passes through a gas, the atoms in the gas absorb specific wavelengths of light, depending on the atom's properties. This phenomenon explained the absorption lines observed in the sun's spectrum, marking a significant advancement in our understanding of the composition of celestial bodies. Thanks to the James Webb Space Telescope, scientists and astronomers have gained a better understanding of the universe and its mechanics. What do you think about the James Webb Telescope's revelation of the extreme outburst galaxy, Messier 82? Let us know your opinion in the comments below. And if you enjoyed watching this video, make sure to give it a thumbs up and subscribe to the channel.